Today is Dr. Prashant Tembere, Professor and Clinician Scientist, Department of Hematopathology, ACTREC, Navi Mumbai. Our chairperson today is Dr. P.D. Subramanian, Professor and Head, Hematopathology, ACTREC, TMC, Navi Mumbai. We have a certain number of students for the session. The students along with attendees and moderators will be
Medical College, Aligarh.
Good evening, I'm Dr. Abhyami, second year PG from Amata Institute of Medical Sciences, Kochi.
Good evening, everyone. I am Dr. Adiba Aziz, TR1 from GSM Medical College, Kanpur.
Dr. Karan Bhatia, are you there?
Karan is not there. Dr. Shrishti?
Good evening, everyone. I'm GR1, Dr. Shrishti from Tirthankar Mahavir Medical College, Moradabad.
Dr. Tejasvi is not there?
Tejasvi is also not there.
Okay. So the moderators of the session are self, Dr. Deepika Chatterjee, Amic Fellow, Cytopathology, and Dr. Samina, Assistant Prof. Pathology, both from KM Hospital, Mumbai. The webinar hosts are Dr. Anita Borges from Center for Oncopathology, Tata Trust, Mumbai, and Dr. Sumit Gujral, Professor of Pathology, Tata Memorial Hospital, Mumbai. Certain reminders: if you face connection interruption, low or no sound, video freezing, or video lag, kindly leave the meeting and rejoin with the same link. If the problem persists, please check your internet connection. Please answer the poll questions if any by typing in the chat box, and please do not send annotation requests for the presenters because it disturbs them. Some disclaimers for the session, kindly go through them. Some more disclaimers. Okay, so for the upcoming talks on the 24th of October, 7 p.m., we have the topic Maturation Patterns in Lymphoid Lineage by Dr. Gaurav Chatterjee, Associate Prof. Department of Hematopathology, ACTREC, Navi Mumbai. And on the 29th of October, 7 p.m., we have AML Morphology by Dr. Nikhil Patkar, Professor, Hematopathology, ACTREC, Navi Mumbai. So with this introduction, let's start. I will stop sharing the screen right now, and Dr. Prashant, the screen, you will start sharing the screen. The stage is yours.
Can you see my presentation?
Yes, we can see.
Yes.
Okay, it's in the full screen, right? It's in full screen, right?
Yes, this is full screen. Yes.
Okay. Hello, everyone. Good evening. So,
sorry. I think you have shared your screen and not the presentation.
Yeah, screen.
Because the next slide is also visible.
Okay. So I have to share my now. I have to share the screen, right?
Yeah, you have to share screen, not the PPT.
Yeah, I have to share entire screen, right?
And the screen should be full. It should be in the PowerPoint show.
Yeah, it was in PowerPoint show, but it shows that way. See, I'm sharing entire screen and share. So when I say entire share, right, and now you can see my screen, like all windows, right?
Yeah.
Yeah. So when I choose my presentation and I'm in full form. So when I put it full form.
Okay. Display settings, just see.
Yeah, we can see you Prashant, you have to share entire screen.
No, you're sharing but it is showing the next slide also. So,
yeah.
So I think something to do with his computer, maybe laptop, desktop. But once he
no, I percentile view. Yeah.
No, but when okay.
No, it is showing the percentile view.
Yeah, it's fine, better now. Just make it full screen.
No, but it's trying to make full screen. It is not happening then.
Make it full screen, Prashant.
Yeah, I'm making it full screen. See, now if I make a full screen,
it shows not full screen. You know, you're not sharing your entire screen, Prashant. You're not sharing your entire screen.
I'm sharing no, I'm sharing entire screen.
No, you share only the PPT.
Are sure?
Yeah. Because since you're sharing entire screen, it is appearing by the way screen appears to you.
Sundar Shivale wants to help.
Okay. I'll stop sharing and again share. See, I have three tabs. Window and entire screen. What do you want me to share?
So window.
Yes.
Show the window and select
okay. PowerPoint. Okay. Now this is the window and PowerPoint. Can you see
make it full screen? Yeah, make it full screen.
It is full screen now.
It is not.
It is full screen for me.
Let me just see somebody. Change in presentation mode. Somebody suggested to change it to percentile.
Yeah.
Change in the presentation mode. Change it to presentation mode and hide the percentile view. It is showing the percentile view. Press F5 to make full screen. Press F5 to make full screen.
Press F5.
Dr. Mani, I think I have to share full screen only, entire screen only. I don't think
then share the screen and see the view in PowerPoint show and don't show it percentile view. In PowerPoint show, don't make it show the percentile view.
See, I'm now sharing full screen. I'm opening my presentation. It is open now. And now, when I do, I'll go to the slideshow, right?
Go to view first.
View.
In that,
you have normal. I selected normal.
Slideshow. There must be slideshow, no?
Slideshow.
Slideshow, yes.
Go to start from the beginning. Click on it.
Yeah. See, when I say from beginning, it shows both next slide also.
Okay. Now it is.
Maybe in display setting is swap, presenter view and slideshow. Now,
Now it is correct. Yeah.
there is a display setting. Okay. Sorry, sorry everyone. And I'll start. I have to say that I'm just taking myeloid maturation because infant maturation is taken by Gaurav. And we have two sections for this presentation. One is I'm going to some theory. I'm going to explain how the things work, what is my maturation pattern, how the normal maturation pattern, how it looks in some disease conditions, and then in the second part we'll go through some cases. So we know we are focusing on myeloid maturation. So we know that how the myeloid cells mature in the bone marrow. For example, let's take a granulocytic series. We know we have the earlier because there is a myeloid blast followed by promyelocyte, right? Then myelocyte, metamyelocyte, neutrophil. Now, based on the and you can see when we see the different differentiation of this morphological maturation. If you look at myeloblast, we have only large nucleus and scanty cytoplasm. We don't see any granules in it. So usually this is the primitives. Many times we see nucleoli also. Then when it comes to the next promyelocyte, the nucleus size shrinks down and the cytoplasm increases. So there is low nuclear to cytoplasmic ratio. Cytoplasm has more granules, right? Then as you move to the myelocyte, again the nucleolus disappear, the size goes down. The nucleus will become more oval. When you come to the metamyelocyte, the nucleus become more kidney shaped. Start shrinking and shrinking so that the shape changes. And when you do the band form of neutrophils, this all chromosomes condense to form a globular nucleus. So these changes happens which are morphological changes. But all structures of cells are ultimately formed by the proteins and carbohydrate and lipid complexes. So when this happening, when the structural changes happen, of course, the 3D architecture of the protein structure also changes, which leads to the expression of antigens on the cell surface or inside the cell. And this protein has epitopes on it, which acts as an antigen, and which has appearance and disappearance, which changes in the number of antigens and in terms of reduction. Some antigens reduces in number, disappears from the cell surface. Some antigens becomes increasing the number, and this way, it changes from one form to another form to next form. Now, these changes in the protein structure can be studied by using flow cytometry, and we are going to focus how the flow cytometry changes can help us to identify normal and to differentiate from normal to abnormal. Now, as I mentioned, ultimate to identify the protein expression, and this is because when we have any changes happens from the nucleus to the protein, which this is the dogma we believe in, where we have transcription, splicing, export, and translation. So all RNA expression leads to the protein formation. Any neoplasm or clonal hematopoiesis, which results from genetic changes, also because it is followed by the formation of protein, also affects the protein formation, and hence the clonal hematopoiesis can have altered protein expression on the cells, and this is because and when we study the protein expression, changes in the protein expression, basically we see the changes in the gene expression, which is a result of genetic abnormalities. And this is how we can identify normal maturation or abnormal maturation as a result of clonal hematopoiesis. Now, this can be identified by different things. For example, cytochemistry. So we looked at cytoplasmic myeloperoxidase. Myeloperoxidase is enzyme. We can identify which myeloperoxidase is increased or decreased. It is present or absent. We can look at it. IHC, immunohistochemistry, to identify proteins by indirect antibody and tagging with the color so that we can see. Then flow cytometry is another technique. Mass spectrometry, where you can lyse the cells, and when you have free proteins, based on the mass of proteins, you can identify the protein in the sample. So these are different techniques where you can. And there are a few more, but these are commonly available in at least in the clinical laboratories. Then there are Western blot, protein electrophoresis. We know that, right? Now, let's understand using a cartoon how when I say protein expression changes, what happens, right? So this is a cartoon where you have immature form. You can see here. We have immature form. You can see some nucleoli and high ratio. Then we have some mature form from one to other of myeloid series. And just showing this cartoon, I'm going to explain how when I say antigen expression increases or decreases, what does it mean, and how it may appear, or how we can imagine it may appear actually when the cells are maturing from one form to other form. So let's say we have three types of protein: protein A, protein B, and protein C. And this protein changes in the density at one stage to another. How about level? So for example, this is a blast where we have certain number of protein A is higher in density. Then we have protein B less in density. You can see there are hardly few proteins, and protein C is absent. Now when we move from this stage to this stage, what is happening is one of the protein is still there, but the density or the number of proteins present on the cells is really reduced. But the other protein density has increased. You can see the antigen density of these proteins increased. Right. So that means when if you put an antibody, so the number of antibodies binding to these cells for the protein A will be more, and number of antibodies binding to protein B will be less, and number of antibodies binding to the protein C will be absent. It will not bind. Now to the next stage, although some of the antibodies will bind, but since the antigen density is lower, the amount of antibody binding to these cells will be low, and the amount of antibody binding to protein B will be more than stage 1. Now if you come to the stage 3, see now at stage 3 the proteins start appearing, and protein A is reducing in intensity, and at last stage you can see that we have two proteins, that is protein B and C and A is absent. So this is how it changes. So if you remove the cell and just focus on the protein, because we are studying the proteins using antibody. So this is how it will look. Your protein A is highest at the density at initial stage, and as the cells maturing, it is going down and it disappears at one stage. Protein B is increasing in the intensity and it is maximum at the last stage, and protein C is appearing only at last two stages and becoming increasing. So if you have different antibodies, these proteins using the antibodies which can bind to the number of proteins present on the cell surface, we can, and based on the density at different stages, we can identify the different stages of cells. So this is an example I wanted to show you so that you understand when I mentioned the antigen density changes and the protein levels are changes. So because the level of what we are looking at, we are putting the antibodies against these proteins which will bind to this protein, and these antibodies are attached to the fluorescence, which we detail by flow cytometry. I'll come to that also. But I hope you understand when I mentioned the density of protein changes from one form to another form, and because this density is tightly regulated by gene expression across the human, all over the earth, we identify this expression pattern of proteins are highly reducible. Their changes to all human beings have the same maturation pattern, and if you have a genetic mutation, right, or genomic abnormality, that can lead to absence of certain protein, that can lead to increase the antigen density of particular protein or reduce the antigen density of particular protein. What will happen? This normal maturation pattern, this normal antigen pattern expression pattern, which moves smoothly from one form to other form, will be disturbed. And if you change that maturation pattern, and that change, because it is deviation from the normal maturation pattern, is a direct indication of genomic events can be used to identify abnormal cells, to identify clonal hematopoiesis, to identify myeloid neoplasm or other neoplasm. Okay. Now, so this is basically, and flow cytometry is a single cell analysis for the patterns of protein expression. We study single cell. So we study antigen expression pattern on cell surface or inside the cell, inside cytoplasm or on nucleus, on single cell at a time. Now, this is very high-speed technology, so we can study millions of cells in few minutes, and thus we can study all these cells, normal, abnormal, different types of cells in very few minutes using the different antibodies against different proteins. Okay, so that's it. As I mentioned, how do we identify normal population and abnormal population? So normally we have these antigen expression consistent because these are tightly genetically regulated, and our genes, our genomics, in our human DNA, our human genetic pattern expression is same throughout the human. So these are highly reproducible, and because they show reproducible pattern with the different maturation of different cell lineages, these patterns can be studied in normal. And because the genetic abnormalities can lead to the deviation of these reproducible patterns, we can detect this deviation and confirm that there are abnormalities, or that this is a clonal hematopoiesis or neoplastic hematopoiesis. Now, when I say how we can study, what are the indications of this alteration? So either you have increased or decreased antigen expression pattern. The second thing, because we can study multiple antigens, and these multiple antigen expression changes simultaneously, there is a synchronous expression pattern. The expression pattern goes hand in hand. So that is called as synchronous antigen expression. So if you have asynchronous antigen expression, which also indicate neoplastic clonal. Now, aberrant antigen expression pattern. When I mean aberrant means you have some markers which are not supposed to be expressed on a particular cell. For example, lymphoid marker in myeloid. That would be aberrant. And because that homogeneous antigen expression, meaning that because these cells are always maturing, so they are moving from one stage to another stage, so there is always heterogeneous maturation, right? Variable, because they are moving from blast to chromolyte to myelocyte to metabolyte, blast to promonocytes to monocytes. So there is always a maturation, continuous process, right? If there is arrest because of the abnormality, there can be arrest because genetic events does not allow for differentiation. That's how the leukemia, for example, in leukemia or lymphoma, there is a reproduction of the clonal, increase the clonal mass because they cannot differentiate for the normal process, normal process, they cannot participate. So what is they form homogeneous antigen expression? That leads to homogeneous antigen expression. So that homogeneous antigen expression also indicates abnormality. Just to show you, this is the carbon on this photo. You can see the increased intensity. When I mean increased intensity, that means something which should be normal, but if it is increased than normal, far increased than the normal, as I showed the picture, where you should have four legs, but if you have 8 legs, then it is increased intensity. The same way, loss of antigen expression. Something which should be there normally, but it's absent, right? So normally the protein should be there, but it is lost. So that also indicates abnormality. Then asynchronous antigen expression, something which should appear at a particular stage, but is not appearing. Right? Abnormal localization of antigen at different stages or different part of cells is also indicative of aberrance. And lineage, as I mentioned, aberrant lineage. That is complete lymphoid antigen expressed in myeloid lineage, or myeloid antigen expressed in lymphoid lineage is completely aberrancy. That is this is a gross aberrancy, so it is called aberrant lineage antigen expression. So these are the common deviations that occurs when there is a neoplastic changes in the myeloid series or lymphoid series for that matter. And we can use this to identify aberrancies and confirm the neoplasm. Now, when we look at the myeloid cell, the myeloid cell lineage has multiple sublineages. Like we have blast, stem cells, right? Then we have granulocytic series, we have monocytic series, we have erythroid series, also eosinophil, basophil, mast cells, dendritic cells, myeloid, parganocyte, dendritic cells, and there are few more subsets which also forms the part of myeloid cell lineage. But these are the common subsets which we see gross morphology very frequently, and also we can see there are morphological abnormalities or dysbiosis in these cell lineages. So we will go through this all different series using flow cytometry. What are the normal maturation pattern? How the normal patterns can be seen. When I say pattern, means how the antigen expression looks like when we study together. So when I say pattern, means when you see more than one antigen at the same time, so 2, 3 antigens, and when they move together in synchronous fashion, they give rise to a particular pattern of antigen expression, and that patterns we study by using flow cytometry. Now, because many of your students, I'm not sure how many of you are in flow cytometer. So these are the different flow cytometers from different companies. There are companies like Beckman Coulter, which provides which provide the flow cytometer. This is how we look. And so next is how do we process the sample? Now, when we want to study bone marrow or peripheral blood or body fluid, we have two types of cells predominant. One is WBC and then RBC and platelet. Now, RBC are very large in number as compared to the WBC. RBC are millions and WBC and thousands. So when we want to study WBCs, we don't want the millions of RBC to be there in our sample that can interfere with the analysis because they are too many in number. So what we do, we lyse the RBC. So we do use ammonium chloride solution, based solutions, lysine solution. We put in the sample that lies our RBCs, and then we left with WBC. Now we take these WBC and we put antibodies which has proteins attached to it. So like this. Now these antibodies are the monoclonal antibodies which specifically bind to a particular protein, uniquely bind to a particular protein. They will not bind to different proteins because they are monoclonal antibodies. And these antibodies, as you see, they are attached with different photones. Now these photones have a tendency to absorb the laser light and excite different wavelengths of light, and which is detected by flow cytometer. I'm sure if you have attended the basics of flow cytometry, you have gone through this. So these antibodies which are proton tagged to them are then attached to the particular antigen, and these cells, after incubation of 10 minutes, are run through the flow cytometer. And flow cytometer has ability to detect these protons, which ultimately detects which protein present on a particular cell, and we can identify multiple proteins at the same time. We can identify 8 proteins at the same time on the same cell. We can identify 16 proteins at the same time, same time. So because we can identify multiple proteins, multiple antigens present on cells, we can study the combination of expression of these markers, which gives rise to the patterns. Now, how flow cytometer work? I'm just a couple of slides I'll explain on that because I don't know how many people of you have attended basic. So when a cell comes in front of a laser, you see this laser light which is present inside the laser is present is built in flow cytometer, and there is arrangement where a single cell comes in front of laser. Now this laser light hit the cell at two places. One is outer surface, and some of the light hit in the inside the cell to the organelles, different organelles of the cells like granules. Now laser light which hits outer surface of the cell get diverted in forward direction. based on the size of the cell. So if cell is small, this diversion is less. If cell is large, this diversion is high. And this light, which is diversion, we determine or we evaluate as a forward light scatter using detectors, forward light scatter, because this is scatter of light in forward direction. So high, wider scatter indicates large forward scatter, indicate large side of cell. Small forward scatter indicates small side of cell, small forward scatter. Now some of the laser light, as I mentioned, hit the granules and it is scattered in surrounding the cell in all 360 degree also. But in first we collect this light from the side of the cell, this scatter light, and this is called as the side scatter. This is scatter of light, and we have collected the scatter of light from the side of the cell, side scatter. Now the higher side scatter is high granular. If there is no side scatter, that means there are no granules. The cell is minimum organelle, and that's why there is no diversion or scatter of this light. For the lymphocyte do not have granules. So say they blast, they have hardly any granules. Myeloid blast can have very few granules, but they have so small number that there is hardly any side scatter. So low side scatter means low granules or granular cell, like lymphocyte or blast. High side scatter means the granulocyte, like neutrophil, promyelocyte, myelocyte, metamyelocyte. Monocytes have very few granules, so they can have some side scatter. So this is how these are physical properties of cell which we can identify by using. So many cell counters nowadays, laser-based cell counters work on the same principle. Now, how to identify protein? Right. So we have this is also a cartoon, and you can see there are different proteins, and consider there are very few epitopes against which we have formed the antibody. Now, since we put antibodies which has protons stacked in, this antibody will bind or binds to these proteins very specifically. And such cell may come in front of laser light hit this proton and give different fluorescence light, and this fluorescence light is detected by the flow cytometer and analyzed by different software, where we know that this fluorescence light is attached to certain antibody, for example CD4. This fluorescence light is attached to the other antibody, for example CD7. And this is how we know that the CD4 is present on the cell, CD7 is present, CD34 is present, or CD50 is present. Different marks. So CD is the cluster of designation given to the particular epitope or the protein present on the surface of different cells. And these proteins, this cluster designation, they are not the same on all cells. Some cells express particular proteins, some cells express different proteins. For example, we know T cells express CD3, B cells express CD20, and myeloid cells express CD13, 33, like that. Now, if you look at myeloid cells, as I mentioned, this is a simple figure. You can see, we know that hematopoietic stem cells, we have hematopoietic stem cell which they differentiate to the myeloid stem cell, lymphoid stem cell, right? And then the myeloid stem cells again differentiate into different lineages like granulocytic, monocytic, erythroid cell, megakaryocytic, and then myeloid cell further get myeloblasts again further get differentiated into eosinophil, neutrophil, basophils, dendritic cells. So this is differentiation, and a part of hematopoietic stem cell difference from lymphoid stem cells, and lymphoid stem cells use different lymphocytes. Now, these are the different markers which routinely used. There are more than 400 markers that have been used, but these are the commonly used in a good laboratory. These are in average center tertiary hospital. You will find these all markers are present, which are used for different lineages. For example, myeloid cells. Usually, we use CD11, CD13, 15, 33, 117, right? CD60. These are commonly used myeloid. Then these markers are also expressed on monocyte. But in monocyte, there are a few markers which are specifically expressed. For example, CD40, which is not expressed in myeloid cells or granulocyte. Then CD163 or CD11C. No, these are expressed. These are also expressed in granulocyte, but very low lineage. 64. These are very highly expressed on monocyte. Then for erythroid lineage, we know that glycopyrene, 371 is strongly expressed, 336 is expressed. These are also different markers. Similarly, megakaryocytic lineage also have 36, 41, 42B, 661, 62. These are megakaryocytic ones. For basophils, we have again LMD13. So you can see the LMD is strongly in majority of the myeloid lineage. Then we also have a specific marker like CD203, which is only expressed in basophils and mast cells. Then we have marker CD123, which is also expressed in basophil, mast cell, and dendritic cells. HLA-DR, which is HLA molecule. Then plasmacytic dendritic cells. So there is a list of markers which is used to identify different cells. Some of the markers are common, some of the markers are unique for particular cells. And these markers change their antigen density when they mature from one form to another form, another form. There are specific lineage markers. We know that there are specific lineage markers. WHO. For myeloid, we know the myeloperoxidase, the lineage specific. For monocytic, we know that we have to use more than two markers. For T cell, CD3. For T cell, we have to use a combination of multiple markers like CD19, 20, 22, 79, and CD. Now, let's focus on CD34 compartment. Do we have any question? If you have any question before I am going to, I can answer, or I can move next to the, particularly the students which are present in this group. If you have any question related to both sides or any decision. Okay, so I'm audible, right? Everyone?
Yes, sir.
Yeah, okay. So I hope you understood what is the normal, how the flow cytometry works, and how antigen expression changes, and how we can study them. So let's start with CD34 compartment, because CD34 is a marker which is expressed in hematopoietic stem cells and blast. Or precursor, basically, you can say precursor or progenitors. To be more precise, progenitors. Now, CD34, we know that it is also expressed in other cells also, like endothelial cells, but let's focus in myeloid cells when we are talking, it is progenitor cells. CD34 is uniquely expressed in that compartment. So when we study CD34 positive cells, that means we are studying the progenitor cell compartment, that is blast or stem cells. Now, if you look at CD34 positive cells, or the progenitors can be again divided into multiple stages. So let's start with hematopoietic stem cells. So we have long-term hematopoietic stem cells, we have short-term hematopoietic stem cells, then we have multipotent progenitors. Here you can see that this is how they work. From multipotent progenitors, we have common myeloid progenitors, or we have common lymphoid progenitors. From there, we can do granulocytic, monocytic progenitors, or granulocytic macrophage progenitors, and we have megakaryocytic erythroid progenitor. And then they are further subdivided into mast cell, eosinophil, basophils, granulocytes, and this myeloid megakaryocytic progenitors move to the megakaryocytic and lymphoid cells. And lymphoid progenitors move to the different lymphoid cells. So when we look at the stem cell, we can look at this part till stem cell, MPP, CMP, MEP, and GMP. So these 4-5 stages, we can see how they mature from by using different antigen expression. Because this is normal hematopoiesis, they form a particular pattern. Then we look at it. But in abnormal, neoplastic hematopoiesis, because of abnormal genetic abnormalities, which leads to the protein changes, can lead to the arrest at particular stage, and that particular arrest to the particular stage can show the protein changes, and the protein changes can be identified by using flow cytometry. Thus, we can identify the abnormalities, underlying abnormalities. So to show you this is the first plot. Now let me explain first plot. These are called the dot plots. You can see there are multiple dots here. These are called the dot plots. So this square window is basically a plot, and these are dots. Now we have two axes. You can see this is y-axis and this is x-axis. And the axis is logical axis. You can see the logical log scales are there. When we say 0, some dots which are present close to 0, you can see this is 0 on both sides, and there are few dots here. So dots which are close to 0 means they have no antigen expression level. So we cannot identify any fluorescence from these cells, and hence they are close to zero on our scale. So cells which are close to dots, which are close to zero, have no expression of this marker or this marker. So CD19 indicates the expression of y-axis, and CD38 indicates expression of x-axis. Okay, and each dot means one cell. So we have got so many cells. You can see here there are almost lakhs of cells here, and this marker that is CD38 and CD19, it looks like it is negative. So as you move from the zero to positive, right? That means there are these cells are positive for this marker. That means this marker, this protein is expressed on these cells. For example, here you can see the blue cells. It is not close to zero. It is moving away from the zero towards one. That means this CD90 antigen is present on the cells, and that's why we are getting fluorescence from the cells. That means this marker is present on the cell. The same as CD38 is present on the pink cells. You can see this is present on this. That's why this is positive. This is positive. Blue cells are positive for 90, and these pink cells are positive for CD38. Now you can see that the two-way connection. So one cell is going this direction. Just to show you. You can see here this direction, right? And one population is going in this direction, right? So this is the maturation. So you can see, or you can say that these cells are going in this direction, then we have this direction, and probably cells are maturing like this. So there can be this type of pattern which is going in this cell. So based on the antigen expression, we know that there are cells which are 38 negative. So if you put the negative and positive order here, like this. So these cells are positive for 90. These cells are negative for both. There are very few events of positive for both markers, and these cells are just positive for CD38. Right. So you can see here, these cells are positive for CD38. So this is now the cells antigen expression we interpret. Right. The same way here, if you say the CD44, this population is positive for CD45. This population is negative for both CD33 and 45. This population is positive for 33 and negative for CD45. And this population is positive for 4. Right. So this is how it looks. Okay. Now let's come to this this expression. So you can see when we look at the cells, the stem cells, so we have earliest component of CD34 compartment, covalent compartment, and inverted stem cells. They are CD90 positive. Now as we move, as the cells mature to the go to this as the CD19 is lost, so CD19 is downregulated. That means this protein is disappeared from the stem cell, and as they mature toward multipotent progenitors. Okay, and at this stage we are studying now two markers at a time. We have CD90 and CD38. So we are studying two markers. So as CD19 is downregulated, but CD38 is still not appear on the cell surface because they are negative. So this stage is multipotent progenitor. So this is we have hematopoietic stem cells which are CD90 positive and CD38 negative. When these cells progress or mature from hematopoietic stem cells to become multipotent progenitor cells, then they lose CD90, but they are not positive for CD38. Now as the cells moves from this to either the combination of committed progenitor, that is either committed myeloid progenitor or lymphoid progenitor, they start getting CD38. So they are CD38 positive but CD90 negative. So we have this type of maturation pattern where we move from one stage to another by using these two markers. These two markers help us to find out the three different stages of stem cell hematopoietic CD30 progenitor, CD34 positive progenitor. Okay. Now, when we look at this progenitor, now we know these are the progenitors which are already well differentiated. Where we using the two additional markers like CD45 and CD33, we can further classify them in 4 stages. We can see here when we look at this population, we can see there are 4 5 clusters we can see. And if I want to show you different color, so we have cluster which is negative for both CD45 and CD33. Basically, these are megakaryocyte erythroid precursors or erythroid megakaryocyte progenitors. We have CD45 positive with 33 negative. This is common lymphoid progenitor. Then we have 33 positive, but 45 heterogeneous. When I say heterogeneous, means it is positive and negative both, right? Variable expression. So these are granulocyte macrophage progenitors. We have again CD33 weak, but 45 positive. These are dendritic cell progenitor. And here the myeloid dendritic cells are present in this population only. And then we have lymphoid progenitor. So we can see that we can broadly, by using these markers, we can differentiate or we can identify different types of progenitor within only CD34 positive compartment. Now, what happens to these cells when we look at again more markers? We are looking at now different cells. So as I mentioned, common lymphoid precursor. Now, because this is common lymphoid precursor, basically common lymphoid precursor in bone marrow, if differentiate to B cell precursor, and very few are precursor which gives us to T cell lineage, they move from bone marrow very quickly to the fibers, and the T cell maturation takes place into the fibers. But B cell maturation and myeloid maturation and NK and T cell maturation takes place in the bone marrow. So that's why we don't see many of early T cell progenitors in the bone marrow. Now, when we look at lymphoid, so how do I know this is lymphoid? Because you can see the CD22 is positive. Here, this is the CD22 positive population representing in the same color. You can see this is the same color, right? The same way when you look at 33 and 117, these B cell precursors are negative for both 33 and 117. Same way it is negative for other markers like 117 and 36, right? So these are the B cell precursors. Now we have erythroid precursors. When I say erythroid megakaryocyte precursors, so you can see these are clearly positive for the one so strong expression of CD71. They also show the expression of CD36. You can see they are positive for CD36, right? And they are losing CD117. You can see they are clearly losing 117 HLA-DR. So the HLA-DR is going to negative, right? They are losing CD33, right? So yeah, but 117 strong, nicely positive population. So you can see the 117 is nicely positive in this population. The same way in myeloid precursor, here you can see the myeloid precursor. Here you can see the myeloid precursor, they are positive for 117 and 33. You can see the 117 and 133, right? Some of them are also showing 123 and they are moving towards the basophil. So you can see some of the precursors are moving towards basophil. So because 123 is strongly positive. The same way, some of the cells also becoming they are also coming losing HLA-DR and gaining CD117 strong expression. These are massive. So this figure just wanted to show you how the different expression pattern changes, and we can study by using combination of these markers, and we can identify different compartments and different maturation among the stem cells. I'll show you next how these different lineages can be studied by using different markers. So this slide shows the expression pattern of different markers. You can see how what are the different markers which are present in myeloid, promyelocyte, granulocyte. So you can see here the myeloid the blast have HLA-DR 34, 117. You can see here. The promyelocyte also has some 117, but shows now there is CD15 available. At myelocyte level, we have additional markers, CD11B. At granulocyte, we have CD16. So you can see the different markers are exist, and at all these 3 stages, these markers that is 34 has disappeared from the lineage, right? So HLA-DR is disappeared. So this protein changes happen. So the same way when the monocytic lineage happens. So this is the figure you can see. Now we have hematopoietic stem cell. When we compare 34, so I mentioned we study with 34. So when we combine 34 and 38, you can see the hematopoietic stem cells have least expression or minimum expression of CD38. As they mature from here to myeloid multipotent progenitor, they gain some CD38. As they express to committed progenitor, that is committed myeloid progenitor, they gain CD38, and then as they mature further, they start losing CD34. So this is a maturation pattern. So when you combine these two markers, you will get this maturation pattern. When you combine CD13 and 117 from the stem cell, we have a combination of different. So you can see the cells which are gaining 117 and CD13 expression. You can see the gaining 117 and CD13 expression. These are the cells which are committed to the granulocytic series, and they ultimately differentiate towards promyelocyte. Same way, we have cells which are losing 117 and gaining 117. These are pronormoblast. Then some of the cells also lose 13 and lose 117. They become monocytic series, right? And B cells or lymphoid series, or we have basophils. So these are the different cells by using CD13 and 117. We can see how we can see the pattern. You can see clearly this pattern: orange population, green population. There is a differentiation in progenitor population. Same way by using CD13, also you can see CD33 is expressed in both granulocytic and monocytic series. So clearly there is a maturation pattern from here to here. The same way when the lymphoid population, it is losing CD33. So using combination of commonly use markers, we can differentiate maturation pattern among the progenitor. This is combination of 13 and 64. As I mentioned, the 13 is lost and 64 gained is monocytic series. Same way, the 116, 64 is gained in monocytic series. You can see the 64 is gained, and again at later stage of monocytic series, 36 is also gained. So you can see 36 is coming positive in this population, in this gray population which include monocytic series. But the same way, the pronormal blast, so 36 is expressing pronormal blast or basophils, and it is negative for 64. So using 64 and 36, we have this pattern where we can see the maturation toward monocytic, erythroid, and basophilic pattern. That's basophilic series. Similarly, using 33 and 64, we can see the pattern, normal maturation pattern among the blast. So when I say progenitor, this morphologically blast. Right, same way you can look at the population where if you use a combination of 123 and DR, you can see the population which are 123 weak and orange population. This is myeloid blast. Some of the cells have become dendritic cell blast, myeloid dendritic. Some have become plasmacytoid dendritic blast. Right. So you can see there's a maturation of this way in this way. Now some of the cells, the blast which lose HLA-DR and become basophils. So this is bad. And both HLA-DR and 123 is lost in erythroid. So you can see there's a different maturation pattern. Same way we're using combination of 203C where which it will express basophils and mast cells. If we have basophils and mast cells, there are some mast cells which are getting 117. So same way you can study by using combination of 13 and 117. So these all maturation patterns by using a synchronous expression of particular marker, either disappearance or either increase in the intensity or reduce in the intensity of the marker, we can identify different maturation pattern in the different cell compartment. Now we are just focusing on progenitor compartment here. And if you want to study, or these compartments are well, these figures are already published in one of the free journal, that is Indian Journal of Pediatric Medical Medicine and Pediatric Oncology Journal, which is freely accessible. All these figures are present in this article. Now, when I say study, you know, you can study these markers. So in our laboratory, we have 16 color flow centimeter where we put all these markers for studying this population. You can see we use 34 and 117 and HLA-DR to identify precursor cell, right? Then we study 45 and 38 to identify early part of precursor cell, that is stem cell. Then we use series 36 for erythroid part. We use 64 and 33 and 14 for monocyte. You see, then out of this 14 and 15 we use for myeloid differentiation, and also as I mentioned, 36, 64, 33, these are for monocytic differentiation. 123 and HLA-DR for BDC and basophil differentiation, because 123 strongly expressed in all these cells, but HLA-DR is only expressed in dendritic cells and it is negative for basophil. So using this combination, we can identify BDC, that is plasmacytoid dendritic cells is positive. 123 and DR both are positive in BDC, but only 123 is positive in basophil. Right? Then we also use some markers to identify B cell, T cell, NK cell, and NK cell using this marker CD90 for early precursor, like as I mentioned, for stem cell. Now, using this markup, we can identify different patterns. As I mentioned, you can see here, this is one of the patterns which we use. These are stem cells which are moving this direction as well as this direction. So this is one pattern. The same way, we have another pattern with 30 and HLA-DR, like this and like this and like this. This is a pattern. Then we have HLA-DR and 38 pattern. So they are moving in upward direction. Again, this is direction, and this is direction. You can see. So there are different directions where the cells mature. By using this combination, we can see the happens. Now, the point I'm repeating this because by using this gate, we can see the maturation pattern. Now, if there are cells which do not follow this maturation pattern, for example, we have cell cluster here, that will be abnormal, right? Or we have cell cluster here, which is not following normal maturation pattern, that will be abnormal. And these abnormalities can be identified by using these proteins and can be seen in floral hematopoiesis or neoplastic hematopoiesis. Just to show you an example, you can see normal maturation pattern is like this, right? This is how normal maturation pattern, or I can mention this is like this. Instead of this, it's starting hematopoietic stem cell and maturing in this direction, right? But if you have a population like this, which is not following maturation pattern, that indicates abnormality or clonal blast or abnormal blast or neoplastic blast. The same way, we know that the cells go like this. If you look at here, in this patient, we have all cells clustered here. There is no CD38 expression, 38 absent. So there is a down regulation of CD38 antigen, which also indicate abnormality. So it should be normal like this, but there is no normal. In fact, instead of like going like this, it is going like this. So instead of like this, it is going like this. That means there is altered maturation pattern of this blast. Same way, we know normally there is a maturation pattern of cells like this in this direction and in this direction, right? So form a reverse of C, a mirror image of C, it will be like this. But if you have population blast, which is not at all maturing, because CD13 antigen is not expressed, so instead of going in this direction, in both directions like this, it is going straight. You know? So there is a loss of pattern. In the same way, there is a loss of pattern, right? There is loss of pattern because there are two clusters. So this is clustering. So there is loss of patterns. That is for either for the asynchronous maturation pattern or clustering. This is all abnormalities which indicates in this population. So there are three examples, 1, 2, and 3 different examples which indicates abnormality. Now the same way in the MDS also, in myelodysplastic, normally we have this maturation pattern of stem cells. So these are stem cells divided again. So with HLA-DR 38, we have this maturation pattern. But you see that there is complete loss of HLA-DR. So when we have 38 MDR, it's supposed to be positive here. You can see this population is completely lost by pattern, and they are all falling here. So the HLA-DR is almost due to negative and 38 is negative. So there is another loss of maturation pattern. Again, if you look at 34 and 117, we know that there is a population which matures like this, right? So we have this maturation pattern. Similarly, 33 also shows this maturation pattern like this in 4 duration. But here you can see 117, there is no maturation pattern, there is arrested maturation forming a cluster, right? There is arrested maturation forming a cluster here, which indicates this one. Now, also you can see the population shows 7 expression, which is a T cell marker. That is, there is aberrant expression of 37 can be also indicates it. So this is the case of CMML, where you can see that in this case, you can see there is aberrant clustering, no maturation pattern by using 117 34, no aberrant maturation pattern using 34 and 33. In fact, we should have some B cell precursor. Like here you can see the peak population, which is 117 negative 34 positive population. This population is absent. So absence of normal B cell precursor is again another abnormality. And overexpression of T cell marker, again another abnormality. This is another case. You can see we should have normal maturation pattern, but here you can see normally we get it like this. But there are clear cut 34 down regulation, so weak expression because you can see it is close to the negative population. This negative population is almost close to this positive population. There is down regulation of 34. There is homogeneous expression of 30. There is aberrant expression of 7. In both these cases, by using HLDR. So loss of HLDR, you can see the loss of. Normally it goes like this, right? So it is not there. There is aberrant expression. There is aberrant. Normally it should go like this in both direction. But the same one is positive 30 positive population, which indicates abnormality. Again, this is the case of primary myelofibrosis. You can see the normal maturation pattern will be like this, but here you can see the clustering. You can clearly see the clustering is there. There is arrested maturation. Here, the overexpression of 336 we can see. Again, normally HLDR is weak or the antigen density of HLDR stem cell is low. But in cases like myeloproliferative neoplasm, the HLDR is overexpressed. So it normally should be here, but they are shifted here. So there is overexpression of this marker, and there is aberrant expression of 336, 41, and 61. These all three markers are also expressed in megakaryocytic marker, indicating there is megakaryocytic blast proliferation and arrest in this primary myelofibrosis patient. Right? Another case of CML. We know the CML is a myeloproliferative neoplasm. So we, although in the chronic phase we have very few blasts, but still these blasts are abnormal because we are dealing with neoplastic or myeloid, we are neoplastic myeloid fibrosis. So normally we have this maturation pattern, but here you can see with HLDR 34 in CML, although the blastic field number, this maturation pattern is lost. Instead of 8, it is like this, which is indicating that asynchronous maturation of myeloid blast. Same way, normally we should have this maturation pattern like reverse of C, but we have this abnormality where you can see 333 is overexpressed in this expression pattern and it is forming a cluster, which also indicates abnormality or maturation pattern of the blast. Here again, normally we have the normal B cell precursor which are clearly absent in the CML, which is again indicating that there is abnormal maturation. Right? There is something called as a leukemic stem cell or the stem cell, possible leukemic stem cell, or the stem cell from where this disease is arising, which can be identified by using markers like CD26. You can see the normal the blast, the stem cell, which is stem cell, which I'm showing in this plot, in these two plots. You can see in these two plots we are looking at the stem cell, which part of it expresses CD26 and 90. These are CML leukemic stem cell or hematopoietic stem cell of CML. Now, even we can see sometimes even in the polysaccharide, we know there is a genetic abnormality that is JAK2 mutation, right? So the JAK2 mutation leads to the abnormal hematopoiesis, especially towards the erythrocytes. But also we can identify some also in some cases erythroid abnormality like clustering here. You can normal maturation like this, but clustering here, then this in the part of erythroid precursor. Again, as I mentioned, we can look at quantitative participation. Normally, we have normally out of all the literature, usually the stem cell CD34 compartment is less than 2%, and out of these 2%, usually we have hematopoiesis more than 5%. But if you have more than 2%, the non-staging marrow, or less than 5% of hematopoiesis also can be seen in neoplastic process, provided that you confirm it with other abnormalities. So normally you can see myeloid blast more so myeloid and erythroid, right? Like this. You can see the 39% B cell precursor, but it goes down below 5%, which indicates down regulation of this one. And which is also these two criteria are seen in myelodysplastic syndrome, and this is when these criteria are included in Ogata score, which is published in back almost 18 years back. The similar finding we can see in CMML also. Right. So let me ask you one question, and you can answer. The students which are present on this in this group can try that. So what is the correct immunophenotypic signature of early stem cell or early precursor stem cell? We have three options: A, B, C. Whatever. Any student can answer.
A, sir.
A, sir.
Yes. The stem cells, because they are 34 positive, they are 90 positive, but 38 negative. So this is the right answer. Right. So let's move to the compartment. As I mentioned, this compartment normal based on this abnormality can be seen. And studying these patterns can be useful for the diagnosis of myelodysplastic syndrome, even acute myeloid leukemia, then accelerated phase or abnormal myeloid blast in CML, other myeloproliferative neoplasm like CMML, JMML, other this one can be useful for the diagnosis. As I already shown this to you guys. This is just to show you another example of down regulation of CD117. I mentioned CML. So this was about myeloid compartment. Now let's focus on the granulocytic compartment. Coming back to granulocytic compartments means we are talking about post-blast, that is promyelocyte, myelocyte, metamyelocyte, plasma, and neutrophil. Right. So as I mentioned, stem cells from the cells to move toward the loose CD34. Here. They lose CD34, and when they lose CD34, they become maturing cells. Right. They lose. They also start losing 117. At early stage, they have some 117 expression, but ultimately after that, they lose 117 to become other cells. Right. So how they are? So when I say after blast, we have promyelocyte. Right. In promyelocyte stage, we have CD13, but CD16, and now we are studying the combination of two markers, that's CD13 and 16. So you can see it's CD13 and 16. So we have cells which are here CD13 positive, right? Which are coming, as I mentioned, which are coming directly from 34 positive. So they become 34 negative. They are 13 positive, but the 16 is negative. And this stage is promyelocyte. Basically, this stage is promyelocyte stage, where we have 13 positive, but 16 negative. Now next stage is myelocyte. At myelocyte stage, our 13 is lost. You can see the 13 is lost. It has become negative, but still 16 is not positive. Right? One marker antigen is lost, but another antigen is not appear. So this is myelocyte, promyelocyte to myelocyte. Now we have next stage where the 16 start appearing. You can see that this is weak expression because it's close to 0. Then it becoming increasing in intensity. You can see that increase up to this level. But 13 is negative. You can see the 13 is negative. It is below 13 is negative. So this stage matches with the early stage matches with metamyelocyte. The late stage matches with band form. So you can see this is band form and these are metamyelocyte. This is metamyelocyte. Next stage we have neutrophil where the 13 again reappears. So you can see the 13 reappears. So this goes like this, right? So this is how they form them. So just using two markers, we have identified promyelocyte, we have identified myelocyte, metamyelocyte, band forms, and or this basically correlates with morphology. Not exactly, but there is a quite synchronous between morphology and this one. Although you cannot say by 100% this is exactly the same stage. So if you saw this cell and look into the morphology, you will have predominantly chromolyte, but some cells which overlap, right? So you can also say on phenotypically you can say this is stage 1, this is stage 2, this is stage 3, and this is stage 4. Now stage 4 is stage 5. This kind of like. Now just to remember this stage, you can see this maturation pattern look like hockey stick or like a sign. Just to remember, when we look at CD13, a pattern of 13 and 16 gives rise to the granulocytic maturation pattern, which looks like a hockey stick or Nike sign pattern. Now, when you look at the other marker combination, LMB and 16, when you have these two combinations, you can see the myelocyte and promyelocytes are negative for both. Right? This you can see this population is negative for both. Now, as we move to the myelocyte, it starts getting 11B, and 16 is negative. You can see this population is here. Right? So this. When it becomes metamyelocyte, the 11, the 16 appears and LMB is increasing. So this becomes metamyelocyte. Then you have become band form and then neutrophil. So this is pattern. So you can see there is this type of maturation pattern like this. You see this is maturation pattern moving like this. So with using LMB and 16, we have this maturation pattern and this maturation pattern. So you can see this combination of two maturation pattern using this antigen expression. So this maturation pattern, it looks like the dog's leg. You can see the dog's leg. Just to remember how they look, right? So this is the maturation pattern. LMB, 60 can give rise to this maturation pattern. To remember, you can remember leg of a dog. Just something to remember. The same way, when you use 13 and 11, we have looked at 13 and 16. Here, 11 and 16. Now let's combine 13 and 11. This also shows this maturation pattern. You can see there is this maturation pattern, and some cells falls back when they are terminal maturity. And even CD15, if you look at CD15, there is this type of maturation pattern, which is consistent because 15 appears at promyelocyte strongly in the late blast, and it is strongly homogeneously expressed. So 15 is homogeneously and strongly expressed, but 16 shows maturation pattern, just like this and like this. Right? This pattern can be remembered like a Dhanurasana or both pose of yoga, where you have this type of maturation pattern. And few cells fall down, you can see here like this. So just important to remember this maturation pattern. Now, when you look at this maturation pattern, in this part you can see this pattern. Here, nice this pattern in this population. So this is from the patient. You can see this pattern. This pattern is complete. It's relatively lost. There is no nice maturation pattern like this, but there are some cells going like this, some cells going like this, and that's why there is a homogenization or loss of pattern. You can see normally we should have this type of cells like shown in this figure, but there you can see there are cells going like this, like there are cells going like this. So there is no nice sharp maturation pattern, but in fact this population at this stage there is a broadening of this pattern because some of the cells has abnormal maturation pattern, abnormal maturation pattern. Similarly, if we have normally should like this, normal maturation pattern like this, but again there is this component which has lost this maturation pattern. Normally we should have normal this 15 or expression, but you can see the 15 is clearly down-regulated. It should be limited to here, but there is no. So it indicates the abnormal maturation pattern in granulocyte trees. Right? This is the case of CML. You can see in CML, you can see the normal maturation pattern with 13 and 16, but we have loss of CD50. So not all diseases show all these aberrancies. Then you can see this when you look at multiple markers, some diseases show, some cases or some patients show some type of abnormality, the other shows other type of abnormality. So usually this maturation pattern is maximum in myelodysplastic syndrome. They are minimum in chronic myeloid leukemia, and that's why we don't see many morphological abnormalities, morphology or abnormalities in AML. In CML, although there is proliferation, strong proliferation, the millions of cells or lakhs of cells, but morphological dysposis is limited, right? And that's why, and the same way, even in the protein expression, we see less abnormality, but we can still see abnormality like down regulation of CD50 or aberrant expression of 56 because 56 again NK cell marker. Normally it is not expressed in granulocyte, but overexpression or aberrant expression of CD56 indicates aberrancy, which is commonly seen in CML CP. Another case of CML, you can see the CML showing normal maturation pattern in 13, 16, 13 LMB 16. You can see this type of maturation pattern, but at the same time there is loss of CD50, right? Then another marker which we see is CD117. CD177 is a chemotaxis marker, which is expressed only in neutrophil forms or band forms. Normally this CD177 protein is expressed in more than 50% of neutrophil, and abnormal loss of more than more than 70% of cells indicates absence. For example, in this case, in this population of CML neutrophils, this last stage of the granulocyte series, there is only 27% of cells shows CD177 expression. That means more than 70% has lost this expression, indicates abnormality. So this was about the granulocytic series. Now let's see monocytic series. Also monocytes, let's say monoblasts. So monoblasts, a small population of myeloid blasts, also exposed monoblasts. And these monoblasts are usually DR positive. You can see the DR positive and 14 negative. Now as they become, next stage, like promonocyte, you can see they start showing CD14 expression. They start getting CD14 expression on their cells, and actually DR starts going down. You can see there is a down, it's becoming lower as compared to this. If you put a scale here, this is positive, this is down regulated, becoming a bit negative, right? Then you combine 13 and LMB. As I mentioned, 13 is present at blast stage, but when it moves to the promonocyte stage, the 13 is lost, but LMB appears. So you can see at blast we have 13 positive, DR positive, but 14 negative and LMB negative. As they become promyelocyte, you can see the promyelocyte stage, they gain LMB expression and they start getting this weak expression of protein and down regulation of HLA-DR. And as they become mature monocytes, they become mature monocytes, they gain CD14 expression. They again gain CD13 expression, and there is increase in LMB expression. So using LMB and 13, you can see there is this type of maturation pattern in monocyte. So these are monoblasts, these are promonocyte, and these are mature monocyte. Right? So these three compartments shows this maturation pattern. The same way we have HLA-DR and 30, we have this maturation pattern by using 14 and DR. So you can see you can consider the S pattern, right, in monocyte. Same way when you combine our 64 and 34, because 34 is only blast, monocyte, this shows this maturation pattern. You can see this maturation pattern. When you combine 36 and 64, you will see this maturation pattern. Same way we combine 64 and 14 will be this type of maturation pattern. Right? So we have this type of maturation pattern when we combine different markers. 300 again, a marker which is expressed in late mature monocyte. Right? So you can see there is a kind of maturation pattern when we combine these markers. So we can see DR versus 14 showing the S type of maturation pattern. Again, U type of maturation with 13 and LMB. Again, kind of reverse of this pattern or slending of this pattern, where you can see the C pattern with 300E and HLA-DR. So HLA 300E and 14. These are different patterns. So remember, you can remember snake or the cobra, where you have this type of pattern, where you the monocyte also can see this type of pattern, right? When it's starting from monocyte to blast. Now some of the cells. Again, there are few cells here which I'll show you in the next slide. This is the next stage of the cells which usually seen in the peripheral blood. Now, when you study the peripheral blood, This mature monocyte can be again divided into 3 parts. You can see by using 14 and 16. This part which is 16 negative, there is a part which shows both 14 and 16, and there are cells, monocytes, which shows 14 negative and 16 strong positive. So we have 3 parts, right? The same way you can have 3 parts using 14 and 14 and 45. Where you have these 2 parts are showing they are separating 1 part, but we have this part which is 45 right and 14 negative. These cells which are 14 negative and 16 negative, these are called the classical monocyte. C monocyte, classical monocyte. These cells which are blue, which are 14 negative, 16 positive, they are non-classical monocyte. And the brown cells which are in between, which are connecting these cells, is called the intermediate monocyte. So we have classical monocyte, non-classical monocyte, and intermediate monocyte, right? And this is how monocytes in peripheral blood shows the maturation, right? So as I mentioned, classical monocyte, right? Classical monocyte, intermediate monocyte, and non-classical. Now, normally the classical monocytes are less than 94%, and intermediate and non-classical monocyte forms more than 6% compartment. That is normal population, right? Now, in myelodysplastic syndrome, or like this granulocytosis on monocytic dysplasia, we see this is normal. This the abnormal, you can see abnormal like this, where you can see the HLA-DR has become negative. So instead of S pattern, it has become C pattern. You can see that it has become C pattern. So there is a loss of maturation pattern. Again, another case, normal like this, instead of normal that, this has become straight. So this is again another case shows loss of abnormal maturation pattern. Okay, so that was normal maturation pattern. Now let's see what we can understood. There is a question. Now I will show there are statements. Which one of the following statement is false? That CD34, CD117, and CD16 are commonly used for maturation patterns of monocytes. Another, CD14, 36, 64 related to DR are commonly used to study the maturation patterns of granulocytes. What do you think? Which is false? Both or none? Or any one of them is false? So the answer is basically both, because monocytes 34 and 117 is usually not expressed in monocyte, right? So using this combination monocyte we don't study. Then again 14 is specific, 64 is marker specific to the monocyte, not to the granulocyte. So both statements are false. Okay, let's move. Now let's do the eosinophil. Now eosinophil is less studied nowadays. We are studying, so we'll go quickly. The eosinophil also shows we identify eosinophil by using siglate 8, 3 to 44, and they show this type of maturation pattern by using this combination. So eosinophils also starts differently from the blast stage, that is from myeloblasts. They differentiate to the eosinophil promyelocyte, eosinophilic myelocyte, beta-myelocyte, and this one. You can see there is the eosinophil promyelocyte. This is eosinophil promyelocyte, where you can see there is a prominent nucleoli and eosinophil. And last again, so using this combination, so eosinophil cells are HLA-DR negative and siglate 8 positive, right? And they also show CD81 expression. You can see you can have this type of maturation pattern with eosinophil. Again, they also express CD193 or CCR3, chemokine receptor 3, this type of maturation pattern. So chemokine receptor 3 are expressed in late stage of eosinophil. So eosinophil can be studied like this. You can see here even the IgE expressed. So you have eosinophils which start maturation gain CCR3, and the terminal part of eosinophil also express IgE, and that's why the IgE level increases in allergic condition. So or in eosinophilia. So you can see these are the maturation pattern of eosinophils like this. So the next question, which marker is for eosinophil?
C.
See, that is right. So because the other 3 markers are also expressed in other population, like 242 expressed in NK cell and myeloid cell, CD81 expressed in B cell precursor and other myeloid cell, CD193 is also basophil as well as eosinophil. So siglate is specific for the eosinophil. And let's go to the next stage, erythroid maturation. Now, erythroid maturation again, we have blasts which are early blast, which are 34 and 117 positive population. So which is blastic population or myeloid erythroid, negative cell erythroid precursors of our stem cells, which express 117, right? So at this stage we have early cells, that is pronoun blast, or the earliest precursor of early pronoun blast. You can see early pronoun blast. They start expressing 105 at the pronoun blast stage. So early pronoun blast express from myeloid blast, they become pronoun blast expressed in 105, and they start expressing CD71. But at this stage, glycophorin A is not expressed. Now, as they become late pronoun blast, they show the expression of there is strong expression of 105, 117, and the CD71 expression increase, and a start the CD235 starts appearing. That is glycophorin. At intermediate cells, the 117 is lost, 105 is increased, and 235 is increased. CD43 has started down regulating. You can see CD43 is starting down regulating, and CD235 has increased in interval. So it is intermediate, and then we have late pronoun blast, where we have strong expression of 71, down regulation of CD43, and strong expression of 235, and negative expression of 105 and 117 and 105. So by using 117, 105, 43, 71, and 235A, we can see this type of maturation pattern. Right. So erythroid cells at different stages can be seen in this normal erythroid maturation can show this type of maturation pattern. Right. If you want to combine again these markers in a different way, for example, 36 and 105, 235A and 105, 36 and 45, you'll get this type of maturation pattern. You see. So you have this type of maturation pattern. There we have at earlier stage 105 is negative, start appearing, become maximum. At this stage 36 is negative, again 36 start appearing, right? And 105 is lost, and 36 again. So this type of maturation pattern. Again with 235 and 105 normal maturation pattern. Again with 45, because we know the 45 usually become negative. So at early stages 235 is positive, but at late stages 35 is lost. So using combination of 45, 36, we can identify different cells. Now what happens in the dysbiotic maturation? In dysbiotic maturation, as you say, normally we should have this level of 117, but clearly there is a large population of cells which shows down regulation of CD71, which is usually seen. You can see in this population is also CD71 is lost. So CD71 is lost, the precursor as well as late precursor. Again, CD105 we should show normal maturation and form should fall into the gate. Clearly there is abnormal down regulation and abnormal loss of CD105. Again, there is abnormal loss of CD71 as I mentioned in this population, especially in this mature population. Right? There is down regulation of 40, 45, 40. There is increased population of early precursor. So this is quantitative because normally it should be small component, but here you can see 84% of early precursor out of total erythroid cells, 84% population is early precursor. In this case, you can see 16.9% of population is like that. There is again loss of CD71, so which indicates that not only there is loss of antigen expression pattern, there is aberrant maturation pattern, but also there is a correction and arrest as the early precursor stage in erythroid series, which also indicates erythroid series dyspoisis. Now let's see a question for our students. We can get which markers are most useful to evaluate these two questions in any case, right? So which you think?
C option.
Yeah, so good, very good. So you are now understanding which are the different markers can be used in different populations, basically in cases. So this is our problem. Now let's see quickly basophils and dendritic cells. As I mentioned, there are multiple dendritic cells, human vessel blood, we have plasmacytoid dendritic cell, we have myeloid dendritic cell, which can be subdivided. Now there are more than these subsets, 6 subsets are there. You can see the different subsets: plasmacytoid dendritic cell, myeloid dendritic cell 1, 2. Then there is AXL positive dendritic cell. Then we have Langerhans cells, monocytic dendritic cells. So there are different classical monocytic. So there are which you can use by using different markers. Basically, 123 plasmacytoid dendritic cells shows 123, 303, 304, which is also called the BDCA2 or BDCA4. Yeah, we're using IC. Then we have myeloid dendritic cell and 144, which also BDCA1. Myeloid dendritic cell 2, which also express 1C or BDCA1. There are different markers. Langerhans cells express 207 and CD1A, E-cadherin, and monocytes we have seen already. So these are the different compartments of monocytes. And as I mentioned, these cells come from stem cells. When we go to basophils, they gain, they lose one HLA-DR and they gain 123. So these are basophils. The same way we have increasing 123, but they retain HLA-DR expression. That is dendritic cell, myeloid dendritic cell. So these are myeloid dendritic cells. These are myeloid dendritic cells. Sorry, PDC. These are PDC, plasmacytoid dendritic cells, and we have basophils, right? Basophils. So these are different cells. This is migration pattern. By using 123, which also express, which is basophils express 123, and dendritics are dendritic cells. PDCs are negative for your CD1 203, but strongly express 123. You can see the PDC and basophils can be differentiated by this marker. Just to show you, these are basophils. You can see these are basophils which are 11C negative, 123 positive, and HLA-DR negative. So these blue cells are basically basophils. These are our basophils, and these are our PDC. So you can the basophil can be confirmed by using 3203, 13, and 11 also shows co-expression shows from the I can see the basophils. Now, what happens in CML? We know CML is again geoplastic or clonal hematopoiesis. Now you can see that these basophils can show the expression changes. So you can see there is a subset of basophils are 193 positive and there are 123 negative. There is a weak expression of 123. You can see that these basophils are showing abnormal loss of 123. So 123 is not showing positive. Again, another case of CML. So there are basophils which shows normal level, but other basophils shows down levels of 123. You can see the 123. These are switches of negative, which is expressing PDC. Right. So you can see this is a clear cut aberrancy down levels of 123. Now PDC, as I mentioned, they express HLA-DR and 123, and can be seen by using different markers. So you can see the early PDC shows BDCA4, and the late PDC shows BDCA3. So you have this is the normal maturation pattern between 303 and 304. Now the PDC, some subset of PDC, especially AXL PDC, also shows the expression of lymphoid markers before say 1 and 56, and you can identify 4 types of cells. You can see there are 4 types of PDC which are negative for lymphoid markers, and some are 4 positive, some are 7 and 4 positive, some are only 7 positive. Also shows 356, and these are the population which gives rise to plasmacytoid dendritic cell neoplasm, and that's why they express 356 and 4. Right. Now we have MDC myeloid dendritic cells. They have weak expression of 123, but there is strong expression of 11C and HLA-DR. You can see this great population in myeloid dendritic cells, which can be further subclassified into 31C and 41. So there is a population which is negative for both, the population which is positive for one and positive for both, and this population which is only 31C. So you can make 3 clusters of the myeloid dendritic cells. So myeloid dendritic cell antigen presenting cells play strong role in, and with strong suspicion we can AML we can identify this. Mast cell. We have mast cells. We know the mast cells. They mature in the blood. They are developed in the bone marrow, but quickly they move to the periphery like GI or skin, and hence we see very few mast cells in the bone marrow. And then also we increase the number. So you can see the mast cell. Some of the stem cells differentiate towards the mast cells. They lose HLA-DR. They lose 34, and they gain strong expression of 117. Become mature in mast cells. They also gain 33 as well as 64. So there is a expression of this. But mast cell can be identified with strong expression of c-KIT or CD117. Strong expression of c-KIT or CD117 and negative expression of HLA-DR is a signature expression and DNA expression signature of mast cells. Okay, so let's see another question about plasmacytoid dendritic cells. Which of the following markers are commonly used for plasmacytoid dendritic cells?
B.
B, right. So you can use B because 123, 303, that is BDCA2 and BDCA4. So this was maturation pattern. Do you have any question? Because we can move to the case study now. So the another PPT, I will come out of this PPT, but I would like to, if Dr. Mani has some comments or students have any question or doubt, we can go to that, or we can move to the next question.
No, Prashant. I think you explained as simplified as possible, so we will continue. Yeah.
Okay. So I have the presentation is different, so I'm going to close this presentation. And I'm going to open cases. Okay. Okay. So case 1. Let's say morphology. Now I want some active participation from whatever you can see. It is fine because as Sumit mentioned, this is not only postgraduate, but this is post super graduate, which is like post BM kind of cases, and knowledge is years of experience. So it is fine. Whatever you understand, it is fine to be wrong, but I want active participation from the students. Let's say we had a 57-year male patient, shortage of weight, business, and patient had a history of alcoholism, which I am not mentioning it, but sound of alcoholism is there, and the CBC showed, you can see the hemoglobin is low, 8.4 gram per deciliter. WBC also looks like low, less than 4,000, so only 3.4,000, and even the platelet is low. So indicates what?
Pan-side.
Yeah. So it indicates like pancytopenia because we have all 3 images, hemoglobin, WBC, and platelet on both sides, indicating that this patient has pancytopenia and the redness, shortness of redness is feature of anemia in a old medication. They had some very low level of splenomegaly, and we had received bone marrow now because we want to focus on the female phenotyping. That's why I'm not going to the morphology much. So we have bone marrow done in this patient already. Outside, so we are looking at outside smear. We have received reference CBC, but not reference smear. So we'll focus on that. Now patient has came to the track for the pancytopenia again. The patient has received some transfusion meanwhile. I think the taxane volume, the history of taxane volume was there. So you can see the patient has hemoglobin has become slightly better, that is 11.3, but the platelet is still low and the WBC count is still low because patient has taxane volume, right? and the bone marrow showed, you can see at this age, what do you think this bone marrow for age of 57 years, almost 60 years? Do you think this is normal bone marrow, slightly hypercellular bone marrow, widely hypercellular marrow, or non-cellular or hypercellular? What do you think?
Hypercellular.
Cellular marrow.
Right, because this marrow we have some fat spaces, you can see some fat spaces, but usually it looks like 50% or 30-40% cellular fat cell and 60-70% cellular, which indicate usually this type of marrow is seen in your 30 to adult with approximately 30 to 40 years of age, not 50 years of age. This is closer view, so there is clearly a increased population. So can you see this one, this closer view? If you look at this closer view, which population do you think is more in terms of myeloid or erythroid, granulocytic erythroid or megakaryocyte series? Yes, you can see there's one megakaryocyte we can see, but if you look at a few granulocyte, and you can see there are this pocket has erythroid cells, this erythroid cell, this pocket is erythroid cell, this pocket is erythroid cell. The erythroid cells close to the macrophages. You can see this is a histiocyte of macrophage there. Here also histiocyte of macrophage there, and the erythroid cells surrounding to this. This is again macrophage and the erythroid surrounding it. So here again erythroid cells, and we see hardly any blast. The mature myeloid cells, there are few. Which population is increasing? This you can see. You can appreciate in this population.
So erythroid.
Erythroid, right? So when your myeloid increase in the cellularity, some component has to be increased. So either myeloid or erythroid. So it indicates that on this morphology, erythroid population. Now I'm focusing on particular population on the cluster. So when you look at myeloid population, if you look at myeloid population, what do you think? Do you think this is normal maturation pattern, or there are some dispersions?
Agranulocytosis seen.
Yeah, so it looks like some granularity probably appears to be reduced because I don't see in this pocket. And again, if you see the normal neutrophil, but you can see the folded nucleus. You can see this cell, the nucleus is completely folded. S-shaped nucleus is there.
Yes.
Again, this type of baby nucleus is there. You can see here there is like this type of nucleus is there. Again, this type of nucleus is there. So clearly there are nucleus showing the multiple folds, which can be seen in multiple abnormalities, like you can see in megaloblastic anemia. It can be seen in CML, right? So this type of features is seen. Do you see? Do you know? Can this type of morphology seen in MDS?
Yes, sir.
Usually in MDS you don't see type of morphology. MDS you see less maturation pattern. So there is either monolobated nucleus or pseudo kind of abnormality, right? So here you have hypersegmentation. You have the nucleus is so much mature. So there is a delay. There is a delay in cytoplasmic nuclear maturation patterns where the nucleus is mature, too much mature, and cytoplasm is not mature. And that's why the nucleus, because the nucleus is maturing faster than the cytoplasm, the nucleus is folding. Because if you put too many, say too much of the nucleus in small bubble, let's imagine you have too many chromatodes in a small bottle. What will happen? It will compress, right? Because you are trying to fit some structure in small closed space. What will happen? It will fold itself, and that happens in megaloblastic anemia because there is this maturation. There is nuclear cytoplasmic delay where the nucleus is matured but cytoplasm is not mature, and that's why the cytoplasm, the same size is small but nucleus is more, and because the same mature nucleus cannot fit into the cytoplasm, it folds on itself. The same thing happening. Even the CML, right? So you can see this type of map of the CML. Now this is another picture you can see. Just to show you, this is from another case of MDS. You can see in MDS this type of maturation. You can see there is no maturation. There is suboptimal maturation. You can see here. There is no hypersegmentation. In fact, there is hypolobulated kind of cells. Now in this patient, because there was suspicion of the myeloid erythroid, there is erythroid hyperplasia. We had to see the CBC. We have not looked at MCV. I think we should look at MCV. So what was the MCV? You can look at the MCV. Was clearly high, right? MCH is clearly high. IDW was clear, close to normal. I would say on higher side, but clearly MCV was high. It was distinct increase. So which indicates that there was it indicates that there is a megaloblastic type of maturation. And when you look at serofolate and B12, you can see the B12 is clearly reduced at the normal level, indicate that there was vitamin B12 deficiency. Now, because it came as a pancytopenia and this was notable, we also look at, I'm going to show what happens, how it looks in flow pattern, right? In flow cytometry. Now, do we have in megaloblastic anemia genetic abnormality? Is megaloblastic anemia clonal hematopoiesis or not?
No.
No, it's not. So when we do not have clonal hematopoiesis, we do not have genetic abnormality. Do we expect protein expression changes? No, we don't see. Other than some receptor like transferrin receptor 371, which can be downregulated in certain anemia, for example, high deficiency anemia. Other than that, this protein expression, because there is no genetic abnormality, this protein expression shows normal maturation pattern. Although on morphology there can be dyspoiesis, but on flow cytometry it may show normal maturation pattern. So let's see on the blast, we can see the blast shows showing normal maturation pattern. There is clear cut maturation pattern on this side or this side. There is a normal maturation pattern. Again, with using different markers, you can see there is normal maturation pattern, which is showing like this. There are some cells are going in this direction, some cells are going in this direction, showing normal maturation pattern, like this, right? Which we have seen in normal maturation pattern. Or here you can see this, they go in this direction, and some cells are going in this direction. We do not have an abnormal activity of CD7 in myeloid blast. So in this patient, we see the normal maturation pattern, right? So again, let's look at other compartments like myeloid compartment. What do you think in normal compartment? This myeloid compartment. Do you see any abnormality? This is patient. Okay, this plot, and this plot is patient, and this is from normal. Do you think there is any abnormality? If you look at maturation pattern, it is showing like this type of pattern, right? This type of pattern, right? This type of pattern, right? So I'm just highlighting the pattern. Do you think there is abnormal maturation or normal maturation? Okay, let's compare this with this one. What do you think? Does it look similar? Does it look similar like
Yes,
this?
sir. Yes, sir.
Yes. Now, like this pattern, second, like this. Does it look similar or abnormal? Different. These two. This plot or this plot? Does this plot look like this? Similar to this?
Yes.
Yes. Now let's see this plot. Does it look similar to this? Although there is some again from a calcium channel blocker, there is a little bit of regulation, not because the EDT. So if you have sample for normal fertility, but does it show abnormalities like we have seen in MDS cases, in our presentation? Do you think there is any abnormality?
No.
So which indicates that this granulocytic maturation pattern is normal. We are seeing even the blast shows normal maturation pattern. Although there was morphological, you can see the type of segmentation, which looks like dyspoiesis, because that is also not normal poiesis. There is also ineffective erythropoiesis was there, or ineffective granulopoiesis was there. Now, if you look at, we have seen that normal neutrophils shows more than 50% of CD117 expression, right? In abnormal maturation, it is showing there is loss of this one, indicating only less than 30% cells shows CD117. Now here 82% is there. Is it normal or abnormal? Normally it is more than 50%, right? So 82% is more than 50%, which is normal. There is no abnormal expression of 177. And same way, the 56 is also not abnormal. Only small population, very small population is 1.2% of granulocytes showing CD56 expression, which is because of it is additive molecule. So you normally more than 20% of CD56 expression consider abnormality. So here again it is also not abnormal. So we have seen granulocytic series did not show any abnormality. Blast did not show any abnormality. Also we did not look at monocytic series, but in this case the monocytic series also showed less abnormal, no abnormality. So this was the case of megaloblastic anemia, where we had vitamin B12 deficiency. And so I started with, I did not share this case with you guys because yesterday there was another case of megaloblastic anemia. So this is just 2 days back case, so I thought I will include. I'll start with something which was normal. Let's go to the next case. We have history of 58-year male patient who had diabetic mellitus and hypertension, had fever since 8 months on and off, multiple rashes on the body, evaluation showed the hemoglobin was low, but count is high. You can see the 15,500, which is high, and monocyte was 8.8%, and absolute monocyte count is increased. So you can see there is a monocyte more than 1,000, almost 1,750, and platelet count is also looks normal. So there was anemia. In fact, platelet is on higher side, count is also low, count is increased, and monocytosis. So monocytosis is anemia within this platelet count in an adult old age patient. This is CBC. You can see CBC hemoglobin looks low now in this patient, 6.1. If you look at MCV, looks normal. No, NCV looks normal. RBC count is clearly low. That means the RBC production is affected in this case. Monocyte level, as I mentioned, WBC count is high, although not 15,000, but increased. Then neutrophil count looks normal, but monocyte count looks percentage is not normal, but absolute count is increased. Here, neutrophil count is also slightly increased in this case. So there is monocytosis as well as neutrophilia, along with anemia in this patient. This is a closer view. You can see the closer view. Peripheral blood, the RBC marker is not well preserved. You can see there are monocytes with some vacuoles in this population. So monocyte I focus on monocytes because it is a monocyte. So you can see the monocyte with vacuoles present because monocytes is high phagocytic cells. So you can see highly active cells. So you can see sometimes vacuoles can be seen. So you can see this small monocyte. So we have monocytes in this case.
There is a prominent nucleoli also.
Yeah, so this no prominent nucleoli. I don't see this is myelocyte immature cell is there. These are not prominent nucleoli. These are vacuoles actually. You can see probably these are centromere sometimes look like vacuoles, but you can see this is just a chromatic changes which there is no sharp marker circular. These are actually irregular cells. So this is just the chromatic pattern. The staining is little darker. That's why it is showing this type of changes. But you can see the same way peripheral blood has immature granulocytes. This is like myelocyte stage. We have seen the myelocyte stage. So this is degenerated cell. This is degenerated cell, but you can see the myelocyte and some use. So I have taken the picture especially on the monocytic rich area. So the patient's peripheral flow was done just to see what is there. So there are different markers. We have seen the monocytic marker we use 14, 64, 33, 16. HLA, these are the monocytic markers which we use. Now we start analysis of the cells. So these are the viable cells. You can see forward side scatter, high side scatter, and last cells are granulocyte, low side scatter, and the forward scatter, high scatter. These are lymphocytes, and these are lymphocytes. Lymphocytes have no side scatter because it's close to 0 and small. So lymphocyte, monocyte, some blasts are there, the monocytes and granulocytes. So we can see these are the different cell compartments by using side scatter, forward scatter, and CD45 can confirm. You can see CD45 strong and no side scatter because no granularity, side scatter. But they show strong CD45 expression. These are monocyte. These are lymphocytes. We have strong 45, but slightly higher side scatter are monocytes, and high side scatter. You can see these are high side scatter. And CD45. These are granulocytes, and we have weak expression of CD45. Here you can see weak and no side cells. These are progenitor cells. So we can use CD45 side scatter. We can identify 4 compartments. Right? Now what we do, we identify this gate granulocyte by another marker by CD24. CD24 is also uniquely expressed in granulocytes as well as some B cells. So you can see these are our granulocytes. These are CD24 negative, but LMD strong positive are our monocytes, and these are our blast as well as lymphocytes. So these are B cells. We can make 4 compartments in using this. Now let's look at maturation pattern. Let's identify granulocytes. What do you think in granulocyte? Do you think any abnormalities in this? In the peripheral blood. So in peripheral blood, you can see in peripheral blood we should see neutrophils. So we can see the neutrophils can be identified by using CD, strong LMD expression and strong CD4. So predominantly they are neutrophils. The immature cells are, but there are few mature cells are present. You can see these immature, which we have seen in morphology, right? On morphology we have seen optical granulocyte, immature granulocyte, we have seen myelocyte metabolism. So here also by flow also you can identify mature cells. Predominantly these are mature cells, but we can see also with some immature cells showing some pattern of maturation, some maturation pattern like this, some maturation pattern like this, right? But they are not all cells. So that's why we cannot comment on the maturation pattern with more confidence because we are looking at the peripheral blood. Now let's look at monocytes of peripheral blood. We identified monocyte by using strong expression of 64 and 13, and we have removed 24 positive. Some granulocytes are there. So we isolated monocyte, and then we look at monocyte. We can see the monocyte we have identified. Monocyte, all these monocytes we identified by using the gate, where we have identified both 64 and 14 positive cells. Now you take these clean monocytes, and then we look at the compartment, different compartment. So do you think any abnormality in this compartment? So we have 3 compartments: classical monocyte, intermediate monocyte, and non-classical monocyte. Again, there is additional marker I added. That is for the slant, which is positive only in a subset of non-classical monocytes. So normally we have non-classical monocyte more than 1.74%. Right. So normal population, this population should be more than 1.4%, and this population, this compartment should be less than 94%. This population, which is 14 negative, 14 positive, 64 negative, this compartment should be normally less than 94%. Do you think this is abnormal?
Yes. Yes.
What abnormality you can see here?
Increase in number of classical monocytes.
Perfect. So we have clear increase in the classical monocyte, which almost 99.7%, which indicates that there is arrest in maturation, and that's why we do not have intermediate and non-classical stage, because there is arrest at this level, and because of this arrest, because there is a clonal metabosis, and because this one. So that means the monocytes are only classical monocytes. Arrest in the state. That's why we do not have intermediate and non-classical as well as this other compartment of non-classical, right? And this is a feature. This is a very classical feature of a particular disease. Anybody knows?
Chronic CMML. Chronic myelomonocytic leukemia.
Perfect. Very good, very good. So it's a classical feature of chronic myelomonocytic leukemia. In chronic myelomonocytic leukemia, we have more than 94% of classical monocyte, and there is marked reduction in non-classical monocyte and intermediate monocyte. This is the first. Now this feature is restricted to the peripheral blood. Now we know there is a chronic myelomonocytic leukemia, and it is a hematopoietic stem cell neoplasm. So there has to be some other abnormalities. In granulocytic series as well as in blast, right? So let's add this because the granulocyte and blast are can be best studied in bone marrow. So we will study bone marrow aspirate. Now you can see the bone marrow aspirate. This bone marrow aspirate. This is megakaryocyte. It's normal megakaryocyte. Let's say that one thing is this was hyperlocated. Yeah, hyperlocated. You can see the multiple lobes, which doesn't look normal, and you can hyperlocate it. Now look at the granulocytes. Do you think this is normal cells? These cells are normal or abnormal?
Abnormal.
What kind of abnormality we see here?
Granulate is lesser.
Hypolocated and hypogranular.
Yeah, so you can see here, if you look at this cell, you can see there are small pockets here, white pockets, if you look carefully, and you don't see granules, right? So that means that this is because of hypogranularity. So because of hypogranularity, this is hypogranular granulocyte, which shows lack of granules, and that's why instead of looking pink or orange, it looks bleached because the granulocyte is green. Yeah, again, the partial hypogranulocyte is bleached. You can see there are some sort of, you can see they're pale. You can see this granulocyte level, these are pale, cytoplasm is pale. This is normal, this normal granulocytes. You can see this population is some granules, but this population there is no granules. That's why it's bleached. That's why this population is bleached, right? Bleached. So there is hypogranularity and there is abnormal maturation. You can see there is no maturation in this nucleus is hyposegmented. You know, there is hypogranular neutrophil, as well as if you this is again hypogranular cell. If you look at neutrophil cells, you can see the globulation is in the neutrophil nucleus, right? Globulation in the neutrophil nucleus. So there is clear-cut dysbiotic features in neutrophil morphology. Again, you can see some of the cells showing abnormal maturation, right? So and this population, what is this cell? INC ratio. Yeah, so this is blast, right? So this looks like a blast. Again, hypogranular cells, dysbiotic population, dysbiotic maturation, right? So some of this is another blast, possibly blast. We have few granulocyte and neutrophil cells, right? This is another population. You can see there are monocytic, some monocytic precursors. You can see this is monocytic precursor. Irregular nucleus, right? This is again monocyte, basically some bad or abnormal myelomonocytic cells. It's difficult to differentiate with monocyte or myeloid cell. And there is mitosis, you can see, right? So the nucleus are some dysbiosis. You can see dysbiotic erythroid cell. So there is a dysbiosis here in this population. Again, dysbiotic neutrophil. This is monocyte. You can see this is monocyte, right? Again, this is monocyte, right? So this is monocyte. So there are some dysbiosis. This is nucleus. There is a nucleus. You can see. So there is a blast. So you can see this type of blast are there. Dysbiosis there. Another feature of dysbiosis there. And you can see there is a monocyte. You can see there is a monocytic precursor. This is monocytic precursor. This is monocyte. This is monocyte, right? This is monocyte. Some shell. This is monocyte. So this is monocyte rich area. And you can see there is a blast which is prominent nucleus, multiple nucleus, but more cytoplasm. So it looks like more monoblast kind of cell, where you have abundant cytoplasm, blast cell, but multiple nuclei. Oval nucleus, there is no folding. This there is folding. You can see there is folding. The fold, right? So this is again folded immature cell. This is dysbiotic large cell. Again, there are folded nucleus in monocyte. So monocytic precursor. So there are some monocytes. Monocytic precursor again. This is monocytic blast. You can see the nucleoli, high density. So there is dysbiotic. There is another monocyte. This is another monocytic myelomonocytic. There are multiple maturation abnormalities. Dysbiotic abnormalities are there. Okay. Now let's move to close the floor. And this is again another tube of the same tube. You can see put say 14, 16 slant, but it also includes other markers of maturation like 13, 16. 13, 11B, 16 we use for maturation. We use 36, 34 area for monocytic maturation. Blast compartment for 34, 117, 38. Hematopoietic stem cell. So the markers are there. Let's look at the bone marrow. Now, if you look at this is site scan formation. Do you think any abnormality in this population? Do you see any gross abnormality? One abnormality which I can identify is in earlier population, in megaloblastic, we could see normal maturation, normal granulocyte, nice cluster of monocyte, erythroid, but here it is it cannot separate. It is continuous. If you do not give the color, it looks same cluster, one cluster, right? The reason is because of hypogranulation, the site scatter is low. So because of the site scatter and monocytes are increased, so there is no clear demarcation between granulocyte and monocyte because low site scatter, which indicates hypogranularity. Because of hypogranularity, there is no clear demarcation, and the site scatter is reduced in this granulocytic population, and monocytic compartment, which is indicated by purple, is increased. Right? Again, the same way, low site scatter. There is no clear demarcation here, and blast, you can see there is a compartment in the myeloid precursor. Now let's look at myeloid precursor. This upper we plot. This is from the patient, and we have for comparison from the normal person. What do you think as compared to normal? So this is normal. You can see this is normal maturation pattern. This is normal maturation pattern like this and this, right? This is normal maturation pattern like this. Do you think there is any abnormality in patient's stem cell compartment?
Yes, sir. Yes.
What in this plot? What abnormality you see in this plot?
So more CD34 positive cells.
More 34 positive population.
Yes, sir.
What else? What we get abnormality? See this normally we don't you see the tapering kind of cells, right? The cells are increasing in size, but here you can see there is a cluster. In this one, there is no normal this type of. Clearly, there is a cluster maturation, right? So there is a big cluster, indicating that asynchronous maturation in stem cell compartment. Now, normally there should be like this maturation pattern. Here also you can see this cluster, which is this 34 negative, 38 degree cluster shows strong expression of 30. There is no normal maturation of this side. So clearly, there is biphasic kind of clusters. Are there two clusters, right? The same two clusters can be seen. So there is instead of like going like this, there is like spectacular pattern, like expect. There are two clusters. So do you think this indicates normal or abnormal?
Normal.
What?
Abnormal.
Abnormal. Right. So Yeah, because the normal maturation pattern is lost, there is clear cut clustering. There is overexpression of 13, loss of 38, right? The same way you can see the normally, this is normal again. Compare this is normal, which is in both direction. Do you think this is normal maturation pattern? You see, normally we should go like this. This is, but this is, you can see as compared to this normal maturation pattern, do you see this? Does it look normal?
No, sir.
This is patient.
No, sir.
No, right? So there is clear cut abnormality, right? Which indicates that these blasts were abnormal. So we confirm that even the blast was small in number, 4-5%, the blast showed clear cut abnormality. Now, when we look at myeloid series, you can see the myeloid series maturation pattern of this patient. Although the morphology shows abnormality, what about the granulocyte series? Do you see when you see peripheral, we didn't see much of non-maturation abnormality in granulocyte series, but you can see there is clear cut that the maturation pattern looks abnormal, but there are few cells which are going this way. You can see there are a few dots. These are not nicely. This area should be upset. There should not be any cells in this pocket. Here, this is the plot. Here you can see this is this plot, right? So you can see when you compare this and this, it's not clear. There are some cells showing the normal maturation, some cells, small components showing abnormal maturation, which in the marrow in peripheral blood we see only normal, but we didn't see normal abnormal because this component is predominantly present in bone marrow. We do not see significant abnormality with this population, but we see abnormality here, and there is overexpression of CD177. You can see some overexpression. So in the 97% population instead of 32, 50 to 80% is 97%. So there was this abnormality in peripheral blood, in bone marrow also. Because we don't see, classical and non-classical, but this population is 91% because we have some immature monocytes, which we don't see in peripheral blood. There is clear-cut loss of maturation pattern. You can see this is normal maturation, but here it has become straight like this, right? Normally we see this type of maturation pattern between 13 and 15, but here there is no population here. So there is also abnormal maturation pattern in monocytes, right? Do you agree with that? Yes. Yeah. So granulocyte did not show much of abnormality, only small population, but monocytes clearly show the abnormality. There is loss of classical monocyte. There is no loss of normal maturation pattern. There is no loss of normal maturation pattern, which is in 30, 15, and 14 in DR. Right? There is no 56 expression, no classical monocyte. So this was the case where we had 2% abnormal blast, right? Which we showed this abnormal, all abnormality which we have described. You can see the morphologically also there were 2% blast, and then there is the monocyte series was increased, 13% was monocyte, and we have given that the monocyte shows abnormal maturation pattern. Granulocyte series the low side scatter, and only one asynchronous maturation pattern that is 13 versus 16, or I think there is later. And because the blast percent is less than 10%, it has been consistent with myeloma, chronic myelocytic leukemia. Their history of 8 months was there. If you remember, 8 months, and the blast percent low, so it has come under the category of CMML1, right? What about cytogenetics? The cytogenetics did not have any abnormality. You can see that all the genetically abnormalities like which come in cases of CML or these are absent. And but on the next generation sequencing, mutation, you can see there were mutation in multiple abnormalities which we have noted in this population. Right, you can see the frequency of this CDM mutation, DNMT3K, RAS mutation. There are multiple mutations, there are almost 6 mutations we identified, which confirms the total hematopoiesis. But this mutation can be seen in many myeloid neoplasm, not only chronic myelocytic. That's why we can, with this mutation, we can just confirm this is myeloid neoplasm. But we have seen there is monocytosis on peripheral blood and CML, and we see very classical feature on flow cytometry. That's how we confirm the diagnosis of chronic myelocytic. Now let's go to the next case. 76-year woman, presented with again shortness of breath, severe anemia, hemoglobin was 3.6, count was lower side, that is you can see the TLC was low, only 4, borderline. So platelet count looks normal. Okay, you can see on the this was case, this was bone marrow. Again, we have